So folks, in this section we want to look at applications of Newton's second law, which is really something you've done quite a bit with whenever you've dealt with mechanics in either Calc 1 or in a physics class. And so we're just going to take maybe some facts that you already know and make sure that we're considering them in the light of a differential equation. So without further ado, Newton's second law says the mass times the acceleration on an object is equal to the sum of the forces on it. So I use F for forces, and we're adding up all the different forces on the object, and the net sum of those will contribute to the product of the mass times acceleration. So how can we think of this as a differential equation? Well, one way to think of this as a differential equation is to think about acceleration as the derivative of some velocity function. So we could say that dv dt then times the mass is equal to the sum of the forces. So that's one useful perspective we want to consider this as a differential equation. And a second one is to remember that the velocity is the derivative of a position function, and so the acceleration of an object can be thought of as the second derivative of a position function if we use s for position. And so here are two different ways we could think of Newton's second law as either a first or second order differential equation, and both of these are handy to utilize. Okay, so the next thing we want to look at is how are we going to deal with this with just a object in free fall. So an object in free fall on the Earth, we could think of the only force that you have on the object is the force due to gravity. So we could say that m dv dt and is equal to just simply the force due to gravity. And so we could say then that m dv dt and the force due to gravity is simply the object's mass times the acceleration due to gravity on Earth. And if we're thinking of g, let's use g is equal to either 9.81 meters per second up to varying degrees of approximation, or you could use 32 feet per second. Again, it's approximations. And so if we use a positive number for g, but the acceleration needs to be downwards, then we're going to lead this with a negative sign, so we get negative mg. And so here we have a nice differential equation that we could solve for mechanics problems, or if you like, we could take it a step further and m d squared v dt squared is equal to minus mg. And what do we notice? In this case, the mass is negligible, or the mass is irrelevant. It divides out, and so we would have the second order differential equation, the second derivative of v with respect to t both times is just equal to negative g. And this is usually where you then start either a Calc 1 or a physics problem, even if you're not considering it a differential equation. So let's go ahead and look at an application of this. And I'm going to get this application started, and then I'm going to ask you to pull the rest of the information from our textbook. So this is pages 94 and 95 of the class text. And you may want to verify your answers to part C here, that you'll have to reference the text. Okay, so suppose we've got a crossbow bolt that's being shot upward from the ground, and if I say from the ground, then it's implied that the initial height, if we're using y for height, that y naught is equal to 0 feet. Okay, and meters. We're using meters here. So it's equal to 0 meters with an initial velocity of 49 meters per second. That is, v naught is equal to 49 meters per second. Of course, folks, when we use that notation naught, what we really mean is the velocity at time 0 is equal to 49 meters per second. And over here we mean the height at time 0 is equal to 0 meters. Okay, so this is a scenario, and you've dealt with these problems before, and we're just going to quickly recap them. So here I'm asking you to set up an IVP using Newton's second law. So there's a couple of different ways you could do it. I'd like to set up the IVP this way, to say that d squared s dt squared is equal to negative g, with the initial conditions that v sub 0 is equal to 49 and y sub 0 is equal to 0. So now we're actually looking at it as some sort of IVP, initial value problem. So we could then go ahead and solve this. So let's go ahead and do so. I'm going to solve it abstractly first, and then we'll just plug in our initial conditions. So if we want to solve this, we can treat this as we could treat the second order as really just this first order, dv dt equals negative g. This is separable, so we get that dv is equal to negative g dt, or we get that v of t is equal to minus gt plus some constant, and we usually replace that constant there with a v naught. So now we've got our initial velocity equation, and then we would say that, well, v sub t, that's really just ds dt. That's equal to negative gt plus v naught, integrating that by separation of variables. Again, even though I've got a v naught there, that's actually just a constant, so we could say that ds is equal to minus gt plus v naught dt. Integrating both sides gives us s of t is equal to minus 1/2 t squared plus v naught t plus s naught, or using our book notation, they use y for height, which is perfectly fine, so we'll do that, plus v naught t plus y naught. And so then we can take our two initial conditions and simply plug them in. Oops, I dropped the g there. Let's go ahead and plug that in. Great, okay. And then we can go ahead and give the unique solution to this IVP as minus 1/2 gt squared plus v naught was 49, t plus y naught, which was 0. And if we use negative 9.8, then we could write this as negative 4.9 t squared plus 49t for our position function. And that would say that our velocity function then, v of t, would be equal to negative 9.8 t plus 49. So you can now answer these next two questions on your own. Find the maximum height of the bolt and find the time that it strikes the ground. If you're having any trouble with this, as I said before, this is question number 94 and 95 in the textbook. I hope this video was helpful, and we will pick up with some more applications in the next video.